Recording is on.
Good morning. My name is François Louchet. I'm a physicist and I've been involved for many years in theoretical physics and in particular in the theory of dynamical systems. The present talk deals with an application of this theory of dynamical systems to biology and in particular to dynamical properties of epidemics, from steady states to ECGs. ECGs are electrocardiograms, these funny things you see here schematically, which you record when you visit your cardiologist. And they also exist in the case of epidemics. And that's what I would like to convince you of. Okay, so in introduction, this work is based on a previous study I published last year, A Brief Theory of Epidemic Kinetics, published in Biology in June 2020, in open access. The present work, in fact, explores consequences on this work on contamination curves. In particular, explains still unexplained features, like such the ECGs I was speaking of previously, and it suggests applications to global epidemic diagnosis. Let's start with evolution kinetics themselves. The evolution equation, this is the equation here I derived last year. X is the proportion of infected people, and this is a differential equation, of course, which shows you how this proportion of infected people, how X varies with time. The X over dt, the derivative, is made of two different terms. Here on the left you have an infection term, and here on the right, recovery term. This is a quadratic expression which can be written alpha x minus beta x squared. In these two terms, well, the first one here, the infection term, varies as the product of the number of infected people, which means contagious people, with the number of still not infected but susceptible to be, 1 minus x, corrected by a immunization factor. And the differential equation can be plotted here. This is the x over dt in vertical versus x, not versus t, but versus x. That's important. And you find this quadratic expression here in the form of a parabola, showing you the derivative value. So if you start from here, from 0 or close to 0, then the derivative is positive and the number of infected people increases. I lost my arrow, yeah, as usual. So the x increases again. The increase rate is maximum there. Then it decreases, but it's still positive, and you end up with, at this point here, again, my arrow escaped somewhere, you end up in A. A is called an attractor because the x over dt is 0 at A, so the system doesn't like to travel further. And in addition, if you depart from the attractor on the right-hand side, for instance, sorry for the arrow, yeah, here it is. If you depart from A on the right-hand side, then the derivative is negative, which brings the system back to A, and conversely on the left-hand side. So A is some kind of potential well in which the system is trapped. Well, so the x value at the attractor, x star, is easily calculated from the above equation. It's alpha over beta. It can also be expressed in terms of R0, which is the well-known reproduction factor. It's found to be 1 minus 1 over R0. This is an interesting point because 1 minus 1 over R0, as shown here in the bottom, is the well-known value for so-called global immunity threshold. However, the traditional argument on which this concept of immunity threshold is based is the analogy with nuclear chain reactions. But in that case, there is no attractor. And you have a sharp transition at R0 equals 1. If R0 is smaller than 1, then you have an exponential decay of the reaction rate, and the nuclear reaction dies out. On the opposite, on the right-hand side, if R0 becomes larger than 1, you have an exponential growth. And in terms of nuclear physics, this is named nuclear explosion. Well, so in our case, in the epidemics case, the situation is slightly different, because R0 depends on both contamination and recovery factors. When a uranium nucleus splits into pieces, there is no recovery for it. It's dead, that's it. But here, fortunately, when an individual is sick, he's contaminated, then he may recover. In most cases, he recovers or she recovers. And then this can be illustrated by this bucket here, where the bucket is fed by an input of water, and the water may overflow on the other side, which is the output. And speaking of epidemics, the input is the new cases, the flux of new cases in the infection box, I should say, and the output is the flux, the rate, recovery rate. An interesting point with this bucket image, which is true in the case of epidemics, is that the input rate is constant, and therefore, and it's balanced, exactly balanced by the output rate, and therefore X in the bucket, the number of people infected in the bucket, is constant. But those people are never the same ones. Some of them recover, and they are replaced by new ones that are infected. So it's not a threshold. Actually, it's not a threshold. They travel through the infection box. And the flux of people through this infection box is a good indicator to manage the occupancy of hospital beds, as we shall see in a moment. So let's have a look from a closer view of the properties of the attractor, looking at cumulative curves. Again, with this bucket, the output rate is constant at the attractor, as we saw. And in order to get cumulative curves, you have to integrate this input rate over time. And therefore, you obtain straight lines, of course. You have a constant input flow, and then the volume increases linearly with time. This is illustrated here with data from our world in data from Johns Hopkins University, Baltimore, where you have the number of the cumulative confirmed cases here in vertical per million people, and this is not per million people, sorry, and versus time. So you have AF1, AG1. The red curve is for Germany, the blue one is for France, and you have here nice straight lines for both countries. That was last summer. So a nice attractor for each of them with a moderate slope. But here, at the end of the summer, the policies were probably changed, and there were some holidays also, and some other changes. And then both countries left the attractor, and after a transient went to a second attractor, AG2 here, and AF2 with steeper slopes, which means that in that case, the hospital beds were more difficult to manage. And France here went to a third stage, AF3, on the top right, with a gentle slope. Okay, so the existence, the observation of these straight lines are clear confirmation of our evolution equation. And R0 may be estimated through the slopes. So let's have a look now at the route to the attractor, how the system manages to reach the attractor. We start from this well-known equation here, the x over dt equals alpha x minus beta x squared. And we try to integrate this equation to figure out how the system reaches A. The best way to do that is to discretize the equation. And therefore, if you take, for instance, unit time steps, dt, then you start with a starting value of x, say xn, and the following step, the x value at the following step, xn plus 1, is given by xn plus an increment, an additional term here, delta xm. And this delta xm, by definition, is the value of the derivative, is the x over dt, which is alpha x minus beta x squared. So you just replace x delta xn here by the bracket alpha xn minus beta xn squared. Okay? Then let's have a look at this plot. This is also a parabola. This function there is a parabola. It's the same as the previous one, plus the xn term. And therefore, you remember that the attractor was found at the intersection of the previous parabola with the horizontal axis. Now, since you have added this xn term, the attractor is found at the intersection of the new parabola here with the line xn, the straight line of unit slope. And this is the attractor here, at which you have xn equals xn plus the bracket. Okay? So let's use this, this figure to figure out how you can meet the attractor. You start here from an x0 value, initial value x0 of the proportion of infected people. And the next value is found here, meeting the red curve. This is x1. You can see x1 here on the left. And x1 is transferred back using the blue line to the horizontal axis. So x1 is found again here. This arrow is hardly manageable. Well, okay, this is x1. So this x1 has been transferred back to x1 here. From x1, you start again coming up to the red parabola to get x2 here. And x2 is transferred back to the horizontal axis, and you start again from x2 to the parabola. You find x3, and so on, and you end up with a kind of staircase, which brings you to the attractor. You can notice that here the steps are larger than there, which means that the infection rate, the x over dt, is larger here than close to the attractor or close to the beginning. So this is quite interesting because several cases can be found in various epidemics, in various stages of the epidemic. Here, this is the previous case where the system meets the attractor in a continuous way, smooth convergence. But if you increase R0, the reproduction factor, then you may find something funny here. You start from x0 and you follow the staircase here, there, and there. And there, when you try to meet again the blue curve, well, you miss the attractor. And you have to come down. You have to come down here to a red curve. And when you reach the red curve here, you have to come to the blue one, and here on the way back you miss again the attractor, and so on. So you, instead of converging smoothly to the attractor, you just describe this cycle, this green cycle here, where you oscillate from an up case, an up stage, sorry, with a x value larger than the attractor, down to a down value smaller than the attractor, and then up again and down again, and so on. Okay? So this is called a bistable cycle. If you increased R0 even more, you should find even more funny things: successive multi-stable cycles, a quadristable state, and so on, and ending up with a chaotic behavior, which should be fairly difficult to manage, actually. And all these features are characterized by ECGs. Let's have a look here. What you expect in the case of the bistable state is a succession of up and down states. The system oscillates between up and down again, and up and down. Okay. What is observed? So from the Johns Hopkins University data, this is an example of a down-up coupled pair. That's a down-up pair. Other examples are found here. We stay in the bistable state. This is the down-up pair I showed you right before. But what happens in real life is that the attractors are not often stable in time. They may drift. And if the attractor drifts up, for instance, along the blue line here, if it drifts in that direction, and if in the meanwhile the system tries to rotate around the attractor, describing the green circle, well, not cycle, sorry. Then you expect that the up down pairs will be deformed, and you should convince yourself, later on at home maybe, that when the attractor is drifting up, then instead of having equally spaced peaks like up, down, in that case you have up, down, and then up, down, and then up, down. But narrower couples, narrower pairs, up, down, and up, down again. And in the same way, in the brown drift case, instead of having up, down, you have down, up, down, up, down, up. Right? So let's go back to the data. Here, you have, following the French curve, you have a down-up pair because we are slightly decreasing. Then you have an increase here. You have up, down, up, down, up, down. In the case of Germany, you have an increasing drift here, up, down, and so on. A decreasing one here, down, up, down, up. This is not always obvious, but I'll speak of that in a moment. And here, if you go up again even further with R0 values, you find quite a strange thing here. So we have an up-down pair, up, down, and then up, down, up, down, up, down, up, down, up, down. I repeat, up, down, up, down, up, down, up, down, up, down, up, down, up, down. This is strange at first glance, but actually it looks very much like a quadristable state in which you describe green cycles like the one on the left, but two different green cycles which are overlapping each other, and this gives this kind of feature. This is very likely a quadristable state. So we come back to the same figure, and we can separate the different sectors, the places of this figure into three different zones. At the bottom here, for a contamination rate lower than 100 per million individuals. You have the Japan case, where you have slowly drifting attractors, but with no ECGs or flat ECGs. This should be a very bad news in human case, but in the case of epidemics, it's rather a good news. Then, if you go up above this boundary, this red boundary, you have these bistable states here, and above this one at say 380 or 400, then you find this funny thing, which is likely to be a quadrilateral stable state. And if you went further, you should have probably multi-stable states and a chaotic behavior at the end. Now, I'd like to mention one thing. In the case of Germany, you go down and down and down, and you cross the boundary here. And if you are too close from the boundary, the up-down or down-up signals may be affected, would be modified. And here you have a down. Where is my arrow here? You have a down peak, and that's it. Nothing else. Here, something smooth, and then up, down, but with some perturbations here. All right. So I come to the conclusion of my talk. This theory dynamical systems approach shows that in the case of epidemics, you have dynamical attractors instead of herd immunity thresholds. So that's quite important. Something else, R0 can be estimated from the attractor characteristics, and in particular from ECGs. For low R0 values, you have smooth convergence to the attractor. This was the case for Japan. Increasing R0 leads to multi-stable cycles, and ECGs are the signature of all these different cycles. And then these findings open a new research field to better understand and control epidemics evolution. Thank you very much for your attention.